All right, getting into part two of this video, on the last slide, we really talked about in general, there's the same setup, whether you're working with categorical or quantitative variables, but we spent less time with quantitative. So let's get into that. So first of all, quantitative is a little more nuanced because there's a divide as to whether you know the population standard deviation or don't, or have some indication of what the population standard deviation is. So this is how it works. We don't know the population mean, so we take a sample to get a sample mean, right? Like I don't know how many sodas people drink a week, right? So I just would take a sample, study how many sodas people drink a week, and try to understand what that number tells us about how many sodas all people drink per week. So we then calculate the standard error using population standard deviation divided by the square root of n. We talked about this in class today. But it really is related to, depending on your sample size, you'd expect that distribution of means to shrink down significantly as the sample size increases. Multiply the standard error by the critical value or confidence multiplier that corresponds to the level of confidence we want. That creates the margin of error. So this is the same setup. Confidence multiplier times standard error. It's just a different equation for standard error because we're using quantitative variables. So again, this is very similar to the last one. Lower limit to upper limit would be your sample mean margin of error minus the margin of error, and the upper limit would be the sample mean plus the margin of error. So here's an example. So suppose a sample of 100 women in the US are asked, how many alcoholic drinks do you have per week? The average is 3.5. By the way, I would not expect this to distribute normally. I'd expect there are a lot of women that don't really drink. There's probably a small amount of women that drink a lot. But maybe it wouldn't be like, oh, it's like some people is 2.5. Most people are 3.5, a little less. I would not expect the distribution to distribute normally. So suppose we know from prior knowledge that the population standard deviation is 9.1. And if that sounds silly, it should, but there are scenarios where this makes sense. The reason I say it sounds silly to me is that if we don't know the population mean, how can we know the population standard deviation? If you're collecting data on the population or doing a census, you'll have the numbers that can give you the population mean, and they're the same numbers that would give you the population standard deviation. But you'll see during hypothesis testing why this happens. So write a 95% confidence interval for mu, the average number of alcoholic drinks US women have per week, as in we're trying to write a prediction for what population mean is. So our sample mean is 3.5. Our standard error would be take that population standard deviation, divide by the square root of n. So that would be 0.91. Z star in this case, our confidence multiplier is 1.96, and that's because you were asked to write a 95% confidence interval. The margin of error would be to multiply these two numbers, which would give you about 1.7836. So the confidence interval would be take your sample mean and subtract that margin of error, and take the same sample mean and add the margin of error to give you your lower limit and your upper limit. So this would end up giving you 1.7 to 5.3. So what does that value mean? We are 95% confident that the mean number of alcoholic drinks consumed by US women is covered by the interval 1.7, 5.3. In other words, we're 95% sure that the actual average number of drinks consumed by all women in the US is some value between those two numbers. Here's the other scenario, which honestly is probably more common, but it creates a big thing. So probably if you don't know the population mean, you also don't know the population standard deviation. So in that case, you're working with a sample mean and a sample standard deviation. So really, functionally, this makes very small difference. You use the exact same equation we used before. You just know that you're calculating the sample mean, use sample standard deviation instead of the population standard deviation because you don't have one. So it would be S divided by the square root of n, or sample standard deviation divided by the square root of n. Here's the rub. What was found over history is that this just didn't work very well. The numbers they were getting were inaccurate, or that if you were trying to create a confidence intervals, they weren't really doing the job. So someone in England created a t-distribution, which is based on the normal distribution. It just says we're going to see more variability for smaller samples. And that confidence multiplier or that standard error alone doesn't really do it or do it justice. So well, I'll show you. The image will do more. I'll go back to this slide, but so the normal distribution, which is on the left here, it's the same whether the sample size is 10 or the sample size is 1,000. The distribution is this morphing shape. It's shaped like a normal distribution in that it's bell-shaped, but it basically says weirder stuff happens with lower sample size. So notice the image for n equals 10 is not the same as the image for n equals 1,000. Notice it shows all the way from -4 to +4. So it's saying you're going to see more variability. You're going to see stuff happening more than 4 standard errors above and below the mean. But by the time you get to a sample size like 1,000, it pretty much is the same thing as the normal distribution. There's going to be like minute differences between the results of a t-distribution test and a normal distribution test with large sample sizes. So really, and then stuff started to work. So once they introduced the t-distribution, they're like, oh, the values actually work and we're getting more accurate results. So here's the deal. As soon as you know that you're working with a sample standard deviation, just click, I'm using the t-distribution. That's all. That's really all that's going on here. Critical values taken from the t-distribution are denoted with a symbol T star because the t-distribution changes shape based on sample size. Critical values are different for different confidence interval levels and sample size. So below list for 95% confidence, there's different numbers. If n equals 10, T star is 2.263. If n is 100, T star equals 1.984. If n equals 1,000, T star equals 1.960. Note that as sample size increases, T star approaches Z star. By the time we got to 1,000, there's no difference between Z star and T star. They're both 1.96 for 95% confidence intervals. So this is just another example of how these things become more and more identical when you have larger. So really, this is just a fix for the variability in small samples. So let's look at how that changes the mean number of drinks. So 9.1 was actually not I mean, we said that's the population standard deviation, but it probably wasn't. The reality is you probably don't have a population standard deviation of that because we've never accurately asked every woman in the United States how many drinks they have for a week. So we couldn't possibly have these numbers. So if we then said, all right, that's actually not a population standard deviation, it's a sample standard deviation. What that means is if S equals 9.1 was a sample standard deviation, it changes the critical value. Our sample size in this case was 100 women. And notice right here it says T calculator. You'll start using this. It's in the same location as the normal calculator, just a different place in that list. And so for n equals 100, this DF, degrees of freedom, it's always one less than the sample size. So if n is 100, we'd use 99. If n was 10, we'd use 9. If n were 1,000, we'd use 999. It's always one less. So the number that goes here is always one less than sample size. And I'm sorry if this is blocked, but what that basically says is that the standard this critical value or confidence multiplier would be would be 1.9842 in this scenario. And to get to 99% of the data, you'd have to go 1.9842 standard deviations above and below the mean. The calculations get a little more complicated because it starts the same. X bar, standard error is almost the same. We just call that a sample standard deviation. And then the T star, you really have to look at, you have to do the calculation of, what the T-score is in this case in order to look that up. Okay, so that ends up giving us a larger standard deviation and ends up giving us a slightly larger interval. But it says the change was small enough. In this case, that actually didn't even change. This is the same interval as we got earlier, because with a sample of size of 1,000, that's not really what the t-distribution is for. So we almost didn't need to use the t-distribution for this. Okay, that's the end of the slideshow. I know it's not a thorough intro, but I'm hoping that gets you going on the content in topic 6 because we're not going to have class. And I wish you the best. Have a good one, y'all.